So let's look at the summary of the principal components technique, principal component analysis, or PCA technique, as we have seen so far. As we just derived it, it's composed of 3 steps. Step number 1, once again, we center the data, which means we compute the mean and subtract the mean from each data point. Now we use this zero mean data set to compute the sample covariance matrix, which is the average of the outer product of each data point. And then we compute the eigenvalues and eigenvectors of this matrix S, and we didn't show this, but this matrix is positive, semi-definite, real values, symmetric, etc. So it has a nice eigen decomposition where the eigenvectors are all orthogonal, and then the solution of the PCA problem involves setting the optimal basis vectors phi1, phi2, etc. as the eigenvectors of S. In other words, B is equal to the V in our eigendecomposition. The geometric interpretation is that these PCA components form an ordered best basis for a given training data set, right? So if you give it some training data, it tries to find an orthonormal basis of size m. Typically, m is less than the dimension of the data, right? Less than d. That best fits this data. Best in the least squares sense. So if I'm giving some point y, and I'm not saying right now whether this y that I'm giving was a point from our training data or not, but the least squares approximation using this best basis that we have, right? Because the space is orthonormal, the coefficients are given by the inner product between the data and the basis vectors themselves, and my sum for I equals 1 through m, right? In other words, the approximation of our original data point is written as here. And if we take as many basis vectors as dimensions, let's say for this case we make m equals d, then we can reconstruct any data point xk as long as this data point was in the original training set. This will work. In other words, xk will equal to the approximation of itself. However, if this point that we're trying to reconstruct, some y, was not in the original training set, then this equality is not guaranteed, unless this y here happens to be a point that is defined in the span of my training data as well. Then it will work.